Hello. Today I wanted to talk to you about the meaning of the derivative. It's a concept that stems from a seemingly innocent question that two gentlemen a few centuries ago, Sir Isaac Newton and Gottfried Leibniz, asked themselves. The question was something like this. So how do you measure how fast you're going? Well, you could consider the distance that you've traveled and compare it to the time that you've traveled in. And that seems reasonable. So if you traveled 60 miles in 1 hour, you could say that your speed was higher than if you traveled 55 miles within the same hour. What we're really talking about here is a quotient of distance and time. I've taken the liberty of making a graph of a fictitious trip so we could really see what it is we're talking about here. The graph is in distance, which is measured in miles, versus time, which is measured in hours. Sorry for the psychedelic colors there, but here's the graph. Sorry also for the little bit of scribble. So there's my graph, and I've marked 2 points on it. I've marked the starting point of his trip at 0 hours, for which he's traveled, of course, 0 miles. And then I've marked the end point of the trip, 1 hour, after which the traveler has gone 55 miles. And we could use those points to measure speed. We could say this. The speed is 55 miles minus 0 miles divided by 1 hour minus 0 hours, which gives us 55 miles per hour. So using that recipe, we measure his speed to be 55 miles per hour. There's actually 2 problems with that analysis though, and I'll cover the first problem. I'm going to mark another point on my graph in red, and I'm going to sort of eyeball where the coordinates are for that. I'm going to say that the time, it's halfway between 0.5 and 0.75 hours, which, if I've done this right, I would say is 0.625 hours. And it looks like in that time, our traveler has covered 45 miles. So if we now use the starting point and this point that I've labeled in red, we would actually get a different speed computation. And I'll mark that speed computation in red. So this time, to measure the speed, we could say, all right, well, the difference in position, or the distance he's traveled, is 45 miles minus 0 miles divided by 0.625 hours minus 0 hours, which gives us a value of 72 miles per hour. So using those 2 points, we get that speed. So how fast did he travel? Did he travel 55 miles per hour, or did he travel 72 miles an hour? And the reality is both of those answers were wrong, because we didn't quite measure speed. What we measured is something related to it called average speed. We measured on average how fast the traveler went. Here's the formula for average speed. Now, if we represent position with x, time with t, and speed with v, we can write an equation for average speed more formally. Here's the equation. What you may have noticed is the thing that we initially called speed, which we now understand to really be average speed, is the slope of a line that connects 2 points on a distance versus time graph. Let me show you the graph that we originally drew, along with 2 lines connecting the 2 different pairs of points we used to compute the 2 different speeds. What we can say then, without belaboring the point, is that there are in fact 2 different ways we could compute average speed. One way to compute average speed is with the formula that I showed you earlier. which is a quotient of the difference in positions divided by the differences in time. The other way is if we have a distance versus time graph, we can plot 2 points on that graph, draw a line connecting those 2 points, and find the average speed by computing the slope of that line, which would represent the average speed for that time interval indicated on the graph. You may recall when we were computing what we initially thought was speed, I said that there were 2 problems with that computation. We now know what the first problem is, that being that we didn't really compute speed, but rather something closely akin to it called average speed. The second problem is arguably more profound, and it's something that both Newton and Leibniz, while working independently, both grappled with. The problem is this: if we use a difference in position divided by a difference in time to represent even average speed, do we have a way of measuring speed at an instant? An instant meaning by definition that there's no change in time. I think we can illustrate this problem really nicely with a picture. Nice car, isn't it? But how fast is it moving? Well, the photo really defines a moment, or perhaps better said, an instant in time, because with a photo, there's no change in time. Since there's no change in time, there can't be a change in position. So is it reasonable to say that the car is going at a speed of 0? Probably not, for a couple of reasons. For one, it completely contradicts our practical experience. We know from the photo it looks like that car is moving pretty fast. But there's actually another profound reason why we can't say that it's going at a speed of 0. And that is, if we say that it's going at a speed of 0 because it doesn't have a chance to cover any distance, because there's no change in time, then if that one moment the car is going at a speed of 0, in the next moment where again there's no change in time, it would be going at a speed of 0 as well. And the moment after that, it would be going at a speed of 0. In other words, for all time, that car wouldn't be moving. And of course, then that would mean then we wouldn't be able to get around. Our cars wouldn't move, period. Not to mention our bodies themselves. So that poses a big problem, both mathematically and physically. How do we grapple with that problem? Well, Newton and Leibniz both ultimately approached the problem correctly by saying that, okay, if we can't compute anything even remotely resembling speed at an instant because there's no change in time, we could do the next best thing, which is to compute an average speed for a very small change in time. And in fact, logically, it would seem that the smaller the change in time, the closer we would be to computing a speed at an instant. There's a concept in calculus called the limit, which for you calculus students, if you haven't recognized it already, the limit forms the foundation for pretty much anything you do in calculus. The limit, informally, we can say, is the value that some function of x approaches as x approaches a particular value c. This concept of a limit was tailor-made for the kind of computation that both Newton and Leibniz were interested in making. All they would have to do to compute an instantaneous speed is to compute an average speed over 2 points, one having coordinates t initial, x initial, and another having coordinates t final, x final, and take the average speed between those 2 points, and then take the limit as t final approaches t initial, and in that way they would end up with an instantaneous speed at the time t initial. I'll show you what that looks like on a graph. Okay, so here's that graph that I promised. So below is the formula for computing instantaneous speed then. The quotient in parentheses, as you might recall, represents the average speed when we look between the 2 points that are displayed on the graph. When we take the limit as t final approaches t initial, essentially what we're doing is we're taking a time interval and we're trying to shrink it down to an instant or a moment in time. We know we can't actually do that, so we're doing the next best thing by taking the limit. Let's now recap 3 key ideas that we've discovered together. The first is that regardless of whether you're computing average speed or whether you're computing instantaneous speed, both of those quantities are rates, specifically the rate of change of distance or position, if you will, with respect to time. The second key idea is that there are essentially 2 different ways of computing average speed. One way is by taking a difference in positions and dividing by the corresponding difference in time. The other way is if you happen to have a graph of distance versus time, on that graph you could plot 2 points, draw a line that connects those 2 points, and take the slope of that line, the 2 points indicating initial position and initial time, and final position and final time. In other words, average velocity, which is a rate, is either the rate of change of distance over time, or it's the slope on a distance versus time graph. The third and final idea that we've discovered thus far is that you could use that notion of average speed to answer the question that Newton and Leibniz were both trying to answer, which is how do you compute instantaneous speed? Essentially, the instantaneous speed is a limit of the average speed as the time t final approaches t initial. One thing that we haven't talked about, though, is if you look at the graph of that, here it is. The secant line whose slope we're taking there is starting to look a lot like a tangent line. And we're going to talk about that in more detail in a minute when we talk about how this discussion of instantaneous speed versus average speed relates to rates of changes of functions in general. Okay, to take that notion of average speed versus instantaneous speed and put it in a more generalized framework, we could investigate what happens if we consider some function of x and investigate the rate of change of that function as x changes. And we could compute 2 things. We could compute the average rate of change of that function with respect to x, and we should also be able to compute the instantaneous rate of change of that function with respect to x. I'll show you a graph of what that might look like. Okay, so here's a graph of how we might compute the average rate of change of some function f with respect to x. When we talk about average rate of change of a function, we have to specify the interval over which we're measuring that average. So here we go. So here's a picture. And the interval that I'm taking is from x equals a to x equals b. So I've plotted the 2 points on the graph to correspond to that, the one point being a comma f of a, and the other point being b comma f of b. And so the average rate of change of that function f on the interval from a to b is equal to the quotient of the difference in values of f at x equals b and x equals a divided by the change in x, which is b minus a. Now, if you'll notice, that formula is effectively the same as the slope of the secant line that passes through the 2 points on the graph. Okay, so now I'm about to show you a graph of how one might compute the instantaneous rate of change of a function f at x equals a. To do that, we take a similar approach. We plot a graph of f of x, and we plot 2 points, one at x equals a comma f of a, and another point whose x value is only slightly different. We'll call it a plus h, and then the corresponding y value would be f of a plus h. And then to compute the instantaneous rate of change, what we can do is we take the limit of the average rate of change through those 2 points. And here's a picture of what that looks like. So the quotient would be the average rate of change of the function on the interval from x equals a to x equals a plus h. And what we're doing is to take the instantaneous rate of change of the function at a, we're trying to shrink that x interval down to nothing. That means then that we're taking the limit as h approaches 0. Notice that that quotient is equal to that below. So we can't actually set h equal to 0 because we would have a fraction whose value is undefined. So we do the next best thing, which is to take the limit as h approaches 0. And that should effectively shrink the x interval down to nothing. And then that gives us the instantaneous rate of change of the function of f at x equals a, which, by the way, it looks like we're taking the slope of a secant line, except now we're taking the limit of that slope as h approaches 0. Now, before I wrap this discussion up in a nice little bow, I want to emphasize an idea that I alluded to earlier when we looked at the computation for instantaneous speed. If you look at this graph, when we take the limit as h approaches 0, what we're trying to do is we're trying to move that point closer and closer to that point. In so doing, when we talk about taking the limit of the slope of the secant line, in the limit, that secant line is effectively approaching the tangent line to the function, that line being tangent to the graph of the function at the point a comma f of a. Taking the instantaneous rate of change of the function has a name in calculus. It's known as the derivative of that function. So here's the notation for that. Okay, so now we're finally ready to state the three different meanings of the derivative. The derivative has one analytic meaning, which is the formula that I just gave you, and it has in fact two geometric meanings. Let's look at the graph again that we use to compute the derivative. Here's the graph. As we said, in the limit as h approaches 0, that secant line is approaching a tangent line. So from a geometric standpoint, the derivative, we could say, is either the slope of the line tangent to the graph of the function f of x at the point a comma f of a. We could also say, from a geometric standpoint, that the derivative is the instantaneous slope of the graph of y equals f of x at the point a comma f of a. So in the next slide, I'll show you a synopsis then of the three meanings of the derivative. Let's now take the derivative of a few functions and explore what the meaning of the derivative tells us about these functions. Okay, to start this process, I'm going to put up the formula for the derivative of f of x. Notice that part of the formula involves the expression f of x plus h. To evaluate that for any function, everywhere you see x, you substitute x plus h and simplify. So for the function we have, we'll next put up what f of x plus h is. Now that we have that expression, we'll substitute it into our formula and complete the computation of f prime of x. Okay, so we found that the derivative of the function was 4. That function being 4x minus 7. It's a linear function in the sense that when we draw its graph, we get a line. Specifically, we get a line whose slope is 4. Remember that one of the meanings of the derivative is that it's the instantaneous slope of a graph. Since the derivative in this case is a constant, it means that the derivative is 4 at every instant, and so the slope of the graph of the function is 4 at every instant. That's not too surprising to any of us who remember our Algebra 1 well. The slope of a line is constant. The slope of the line that we were using, in fact, is 4, and so that's exactly what the derivative is telling us. Now, from an analytic standpoint, we said that the derivative is the rate of change of the function. Since the derivative is 4, what it's telling us is that the function goes up by 4 units every time x goes up by 1 unit. We'll do the same type of analysis with one more function. We'll look at a different function and take its derivative and see what the derivative tells us about the function itself. We'll next show step by step how that derivative is computed. Okay, so let's talk about the derivative of this function from an analytic point of view, which is the rate of change of the function with respect to x. We see that unlike the linear function that we previously investigated, the derivative of f of x equals x squared changes as x itself changes. The derivative is negative for negative values of x, which means that the function is decreasing for those values of x. Everywhere x is negative, the value of the function is decreasing. Whereas for positive values of x, the derivative is positive, which means for all of those values of x, the rate of change of the function is positive, which means that the function is increasing for positive values of x. At the point x equals 0, the function is at its minimum value, which is 0 itself. And at that very special point, the derivative is 0, which means that for that particular value of x equaling 0, the function is neither increasing nor decreasing. Later on, when I post a video about a particular type of problem known as an optimization problem or a max-min problem, we'll see that those points where the first derivative is equal to 0 are very special points in the analysis of those types of problems. Okay, now we'll take a look at the derivative of x squared from a geometric or graphing standpoint. And to do that, I've made as best a handwritten graph of x squared as I can. And I've also highlighted a couple of points. You may recall that from a geometric or graphing standpoint, you could say that the derivative of a function is the slope at a single point, or it's the slope of a tangent line to a point to the graph of the function. So here's the graph. And what we can see, and I've highlighted a couple of points, one of them being the point -1, 1. The derivative itself, as we talked about previously, is 2x. So at the point -1, 1, the derivative would be 2 times -1 or -2. And so the slope of the line tangent to that point is itself -2. Now, if we look at the other point that I highlighted, the point 2, 4, there x equals 2, so the derivative would be 2 times 2, which is 4. And so the slope of the tangent line to that point on the graph itself is 4. Well, I hope you enjoyed this video, and I hope also that you found it useful and informative. If you'd like to see more videos like it, you can go to my YouTube channel, The Math King LLC, or you can catch the links to the videos on my website, www.themathking.com. Also, you can contact us through our website if you'd like some personal tutoring in any subjects of math. Thanks for watching.